Everybody got your quiz answers inputted by last night? Chapter 2, right? Chapter 2. Okay, we'll get started here. Let's review a little bit where we left off. And we left off, we talked about whether or not something is soluble. It dissolves in water. And for that to take place, water is going to come in and surround the crystal ion structure. And we know that water is polar, meaning that it does not share these electrons equally. So oxygen pulls these shared electrons here towards itself, or more specifically, it pulls hydrogen's single electron away from hydrogen. And therefore, we know that the oxygen part of water is negatively charged, partially negative, and we know the hydrogen is partially positive. So with that, they are going to surround these ions with that specific opposite charges that attract each other. And as they're shaking around in there and moving, they can overpower the attractive force in the ionic structure of potassium and chloride. If water can move around enough and overpower this attractive force, it's going to split up into ions that you cannot see with the naked eye. And it just, we say it dissolves. Now, all of these salts dissolve to a different extent. You know, it's 100, you have 100 grams of water. The question is, well, how many grams of this can you get dissolved? And it's a certain number for each salt. They're all going to be different. And typically, if you raise the temperature, you should get more to dissolve, right? That would make sense. That's not the case for everything. Then, if it dissolves, if we get a bunch of ions in solution, we call that a strong electrolyte. What is the effect of that? Is you can just test it, is you are going to get electricity to flow through the solution very easily if you have lots of ions in solution. And if you have very any ions in solution, you're barely going to get any electric current to flow through there. Now, just common water has different ions in it. If you live out in the country and you have a well, you may have more iron and magnesium and stuff like that naturally in your water. That would cause somewhat electrical current to flow through. And this is copper 2 chloride. Notice the size of the atom or ion difference. This is copper 2. This is the chloride. And again, you have the same situation. Here is the negative chloride surrounded by the positive hydrogens. Well, wouldn't it be nice to just know which ones, just look it up, and there is some cheater charts back here. And I've got one on the pink sheet, but here's another cheater chart. I'll call it a cheater chart, I guess. If you grid this out, it tells you whether or not it is soluble. And soluble, we will put AQ. if it's soluble. If it's insoluble, we're going to have solid. But OWL in our textbook uses this. So if you printed out that supplement I emailed out, I don't know, last night and before, I guess. It is this solubility rules table here that we follow. So looking at this and reviewing what we talked about last time, the question is, which one of these dissolve? And the first thing you should look for is nitrates, potassiums, sodiums, group ones, lithium, potassium, rubidium, lithium, potassium, sodium, rubidium, cesium. Group one salts are going to dissolve. And nitrates are probably the two quickest ones. So this is a nitrate, this is going to dissolve, and that's a sodium done, that's for sure. Quick, quick, quick. Now, OWL is going to have you do this. Solid. I don't know if it puts H2O over this, but when this dissolves, we are going to get Ca2 plus. That's the way OWL is going to want it, and you just click on the AQ. Then you are going to get 2 nitrates. So this is how OWL is going to want it. All right. Sulfates, typically sulfates are soluble. And of course, it is chemistry. There's got to be exceptions, but all sulfate salts are soluble except those containing calcium, silver, mercury 1, strontium, barium, and lead. So we got calcium there. So the answer to this is no. Aluminum hydroxide. There are specific hydroxides here. And hydroxides and oxide compounds are not soluble except those containing sodium, potassium. This would be lithium as well. Group 1. But sodium, potassium, group 1 compounds are going to be soluble. But this is not a group 1 sodium, potassium, so the answer to this is no. Then we have sodium sulfide. And there is a sulfides on here that says sulfide salts are not soluble except those containing sodium, potassium again, group 1. So this would dissolve to 2Na plus aqueous plus S2 minus aqueous. Now listen, listen, listen. You can't make up ions. You have to split this up into ions that exist. Here's what students do. This does not exist. There is no such thing as an Na2 plus. The only thing even close is mercury 2 plus. That does have 2 hooked together. This does not exist. Do not keep that connected. You actually get 2 individual ones to split up. Okay, so that's what we're going to continue with today. Try to be able to interpret those solubility rules, and in OWL, you can actually pump them up. Okay, so we have a table like this. I think this came right out of your book. Solute in aqueous solution. Solute, pretty much what's being dissolved. If you have an ionic compound, it's going to start with a metal ion. What's a good example of that? Table salt. Table salt, ionic compound. Look at the arrow, boom, straight, strong electrolytes. You're going to get lots of ions in solution. If you have a molecular compound, just think of this as non-metals is the best way to think of it. You got non-metals that make up the compound, not starting with a metal ion. So you could have this. Well, actually, I'm going to put it down here. You can have weak acids and weak bases. So for a weak acid, that or this is the same thing. I got a point. I'm going to keep pointing that out. This is hydrogen acetate or acetic acid. If you write it this way, this is the hydrogen that we're talking about, or this is the hydrogen. So you see it both ways. I think Al likes to use this. So vinegar is a weak acid. What does that mean? You're going to get few ions in solution. Now, what ion are we talking about? Well, let's go over here and we're going to write it out. If you have a strong acid, HCl, HBr, and HI are the binary ones. In fact, let's look at that. Grab your pink sheet. I've got that on the pink sheet, whether or not you have strong acids or bases. And it states it right here. Binary acids, HCl, HBr, and HI are strong. All other binary acids and HCN are weak. Let's go down here. Oxyacids. General rule, strong if two or more oxygens than hydrogens. For example, H2SO4 has two more oxygen than hydrogen. Strong acid. HNO3 has two more oxygen than hydrogen. The rest of these are going to be weak. Now, for an acid. So, some oxyacids. If you have a strong acid, what we're saying is this. For example, HCl. %, you're going to get, this is what Al does, H plus and Cl minus. And I don't like the way that went way over there, but you're going to get H plus and Cl minus. 100% of this is going to split off. If you have a weak acid such as vinegar, very few of these hydrogens are going to come off. Very few ions. Less than 5%. What is vinegar? 2.8% or something like that. Most of the hydrogens are going to stay attached. Therefore, you get few ions in solution and you have a weak electrolyte. So if you have a non-electrolyte, something like this, C12, H12O6, or even CO2 in water. So in summary, what happens for a strong electrolyte? You get a whole bunch of ions in solution. Weak electrolyte, you get few ions in solution. And for a non-electrolyte, virtually no ions in solution. Okay. Here's section 3.5 of your book when it's summarized. We know a balanced equation derived in the usual fashion is called a molecular equation because it doesn't explicitly represent the ionic species that are present in solution. when ionic compounds dissolve in water, they may dissociate. That is, when they dissociate, splitting off from the crystal structure. This is the process of dissociation. Into their constituent ions, which are subsequently dispersed homogeneous throughout the resulting solution. Explicitly representing all dissolved aqueous ions results in a complete ionic equation. Two chemical species present in identical form on both sides of the arrow are called spectator ions. These ions, whose presence is required to maintain charge neutrality, are neither chemically nor physically changed by the process, and so they may be eliminated from the equation to yield a more succinct representation called the net ionic equation. So we're going to do that on the next page. We're going to put stuff in these beakers to really try to visualize what is happening. So an aqueous solution of barium chloride. So first of all, how do we write out barium chloride? We have Ba 2 plus Cl minus 1. So BaCl2. And the other one is sodium sulfate. All right. The mixture reacts to yield a precipitate, a solid of barium sulfate. Write a balanced, complete reaction, molecular equation first. All right, so here's what we are going to do. I'm going to use black, and then I'm going to highlight here. So we're going to start way over here. We have barium chloride. Aqueous plus sodium sulfate. Now, we know that they are aqueous, and here's what we need to do is, well, let's put them down here in the beaker first. If those split up, what do they look like in our beaker down here? So if I draw a line, or I draw a squiggly, I want to make this beaker half full, and I have Ba floating around in here, 2 plus, and I have Cl minus and Cl minus, if this is aqueous. And I'm going to color these. Keep track of them. In the other beaker, floating around in there, I'm going to make the beaker half full, is sodium. 2 sodiums right here. Then I'm going to have 2 sodiums and a plus, and a plus, and I've got sulfate. Sulfate floating around as 1 unit. And I'm going to make my sodiums green. And I'm going to make my sulfate blue. So that would be what would happen. I could sprinkle in these as solids and they're just going to dissociate into ions, right? They would be split up into ions. Now, here's my question. When we dump these together, which we are going to do, when we dump these together, would you agree that the positive ion in this beaker can hook up with the negative ion in this beaker? And vice versa, the positive ion in this beaker can hook up with the negative ion in this beaker. Right? That's what we have to consider. And we have to consider is the attractive force between the positive ion in this beaker and the negative ion in this beaker so strong that water cannot keep them split apart, and they're going to form a solid. So in order to consider that interaction, what we do, this is called a double replacement reaction, is we switch the positives. So I draw something like this. I'm saying barium is going to take the place of sodium. Sodium is going to take the place of barium. So if barium takes the place of sodium over here, I now am going to have barium sulfate. Now I am writing this according to the ions. Plus, I am not going to have, now my sodium is going to go where the barium is. My sodium is going to go with the barium. I am not bringing a 2 over. There's no such thing as an Na2 ion. It's a sodium. So over here, I get sodium. Sodium is with the chloride. Cl plus 1 minus 1. And the question is, we know for sure that this is aqueous. It's a sodium. Is this still aqueous? Or is barium sulfate going to form a solid? We are going to get a solid. We need to balance this pig by putting A, due to the 2 sodiums over here and the 2 chlorides. We put 2 right there. Now, what we do for a complete ionic equation is we split everything up into the ions that you see when they dissolve. And we're going to need lots of room for this, so we're going way over to the left here. We're going way over to the left. Barium in a solution for a complete ionic is going to be Ba2 plus aqueous plus. How is Cl2 going to be in solution? It is not going to be a Cl2. There's no such thing as a Cl2 ion. It is going to be 2 chlorides plus 2 sodiums plus sulfate all I've done is split up anything that's aqueous into the individual ions. Then on this side, I am going to get barium sulfate has to stay together. And over here, I am going to get 2 sodiums and 2 chlorides. So let's dump them together.
So if I dump these two beakers together, I'm going to make this beaker full way up to here because these are about half full. And here's what I'm going to have. I am going to have a precipitate that if we let it settle out on the bottom here is going to be barium sulfate. Barium from one beaker is getting together with sulfate from the other beaker. Right? This barium here is going to get together with this sulfate here. Water cannot keep them split apart. We are going to get a solid. The rest are still in solution. So what is still floating around in this solution that do not hook up is Na plus and Cl minus. Isn't this exactly what we're really talking about? So what we do is we just, in our equation, we switch the positives and then we analyze that new interaction that can take place. And if one is a solid, it's going to show up, fell to the bottom. The other aqueous ions are just going to keep floating around in solution. If you do not create a solid, you're just going to have a bunch of ions floating together, right? Floating around. So let's see now. Let's deal with these. These are not really part of our net ionic equation. They are in there to keep charge neutrality. So we can eliminate spectator ions. What are spectator ions? All you have to do is look from one side to the other, and they're exactly the same. Now, here's my sodium on this side and my sodium on this side. Exactly the same. So I just do a dash circle typically like this to see that it matches. This matches. Exactly the same on both sides. And then the chloride. And here's my chloride. And what I like to try to do, it's kind of like having a 2x and a 2y on both sides. You can eliminate them, right? So what I like to do is try to put a light x over it. That one wasn't so light, but I tried to put a light x like this and a light x like this as best I can. I can eliminate those then as my spectator ions. Those are my spectator ions, and what I should be left with then is a net ionic equation, and my net ionic equation is Ba2 plus aqueous plus SO4 2 minus aqueous, and get barium sulfate solid. this barium sulfate solid is going to be called a precipitate. How do you know if you're going to give solid? Once you get to this step, leave this parenthesis empty and look on your solubility chart or your solubility rules. Okay? So the reason that we switch the positives is to compare the interaction that can take place. Can this positive ion get together with the negative ion? So we just switch the positives. So a precipitation reaction is one in which dissolved substances react to form one or more solid products. Many reactions of this type involve the exchange of ions between ionic compounds in aqueous solution and are sometimes referred to as exchange reactions or double displacement or double replacement or metathesis reactions. It's all the same. What do? Switch the positives. I think your textbook uses this old term. The extent to which a substance may be dissolved in water or any solvent is quantitatively expressed as its solubility, defined as the maximum concentration of a substance that can be achieved under specific conditions, temperature, and pressure. Units of grams per 100 grams of water. So these solubility guidelines are the same as these. And there is a distinction down here. Soluble compounds are defined as those that dissolve to the extent of at least 1 gram or more per 100 grams of water. Not soluble compounds are further classified as slightly soluble. If it says slightly soluble, it is not soluble. We treat it as not soluble, which dissolve to the extent of only 0.01 grams to 1 gram in 100 grams of water. Well, pretty much no brainer insoluble ones, you just hardly anything dissolves, right? Hardly anything dissolves. Okay, let's do what a couple OWL questions look like. So if you have this supplement, and do I have it on the next page? Because this will allow you to get through OWL part 1. Got some problems to work out here too. We can do the ones in, we can do these in the next page first. All right, we'll check out a couple here and then I'll do this one too. In each of the following cases, aqueous solutions contain ionic compounds indicated are mixed, right, balanced, Net Ionic Equation for reactions that occur. So we'll just do this first one. We're going to switch the positives. So if we do this first one here, we're going to end up with calcium. It's going to be with the phosphate. And 2 plus and 3 minus. So we're going to end up with 3 calciums and 2 phosphates. If you're not sure if it's soluble, just leave it blank for now, right? And then sodium. Sodium is going to take the place of calcium, so we're going to end up with sodium chloride plus 1 minus 1. This for sure is aqueous. What about calcium phosphate? Calcium phosphate, calcium phosphate. And it's the bottom one. Carbonates and phosphate salts are not soluble except those containing back to sodium, potassium, ammonium. So we know that this would be a solid. Then we would need to balance this equation now. And we can start with phosphate because that's a polyatomic ion. 2 phosphates. Here, this would give us 2 phosphates there. And then that makes 6 sodiums, right? 6 sodiums, so we put 6 sodiums here. Now, can we decipher what the net ionic is going to be out of this without doing a complete ionic? So we know that we are going to get calcium phosphate over here. Oops, I gotta finish balancing that, don't I? 3 calciums, right? 3 calciums there. My net ionic, without writing out my complete ionic, is going to be this. Three calciums right there. Plus 2 phosphates. All right, let's go to the next page. There's one we can do. I call them an ugly olive question. Really, the meat and potatoes of ionic equations is these type of double replacements to see if you create a solid. I mean, that's pretty much why we do that. Here are all these examples right here where we can create all of these solids. But in OWL, we've got a situation like this. So we'll do a few OWL questions to finish us off here. And that should get you through part 1, I believe. It says when aqueous solutions of potassium fluoride, so I'm just in the regular learning guide. So potassium fluoride +1 -1 are mixed with potassium nitrate. So hopefully you've got this one memorized. Potassium being +1, nitrate being -1. Hydrofluoric acid results. Now, this is HF, hydrofluoric acid results. You have to ask yourself immediately, is this a strong or weak acid?
You don't have this question.
Oops, you don't. Well, did I? You don't? Yeah, you do, don't you?
I have to update it, but I don't have it. I don't know.
So this must be a mid-updated one. I messed up. Well, let's write out, where could you write it out? Find a place to write this. When you get to here, let's write this reaction out. It's not in the supplement, is it? You don't have that one, huh? No, it's not the other one either. See if you can jot it down on the back here, potassium chloride and potassium nitrate. I thought I pulled that out there. My apologies. So we're doing KF plus NO3, KNO3, if you can write that out. And this is going to be my arrow. We're going to get at least this. And the question is this strong or weak? And this is a weak acid, right? Which binary acids are strong? HCl, HBr, and HI. So what that's saying is, since this is a weak acid, that needs to stay together just like a solid. Write the net ionic for this. So we're going to write this thing out here. So for this reaction, we are going to get K plus aqueous, F minus aqueous, K plus aqueous, NO3 minus aqueous. HF stays together as aqueous over here. It is a weak acid. That is a weak acid. So what else do we have left then? So if we do this as double replacement, are they both potassium? Yeah, there's a whole bunch of potassium floating around in here. So we're still going to have K plus and there is, oh man. How about this nitric acid here? I was wondering where the hydrogen's coming from. Nitric acid, strong or weak? Let's write the formula out for that. Boy, I missed that completely. My bad. Hydrogen nitrate, strong or weak? This is strong acid. Why is it strong acid?
Two more ions.
You get, yeah, 2 more oxygen than hydrogen. Oh, boy. Okay, so that's strong. What that's going to look like in solution, what Al does is this. This is going to be H plus and NO3 minus. So I've got a big mess here. I apologize. Let's just write what Al is going to look like out of this thing. What's going to happen here is they're going to have this H plus aqueous. You're going to have an F minus aqueous. And it is going to keep the weak acid together as HF aqueous. The other box is going to be blank. So if you have something involving an acid, strong acid, the hydrogen is going to come off, a weak acid is going to stay together. My apologies, I made a mess out of that. Let's go to this one here. This is another OWL question.
So this is the supplement I emailed out. So the first question on this one is, what do you have for ions here? There is no charge. This is a chunk of solid zinc. This is copper 2 sulfate. This is zinc sulfate. And this is solid copper. So we would call this actually a single replacement reaction. Single element replaces another one. If you do not have the same ion charges on both sides, we're going to get a net ionic equation. So let's see what we got here. I'm going to write it out right down here. So you have zinc solid plus, if this copper 2 sulfate is aqueous, that is going to be Cu 2 plus aqueous, SO4 2 minus aqueous. This zinc sulfate is aqueous, so we're going to end up with Zn 2 plus aqueous plus SO4 2 minus aqueous plus copper solid. Now, what is exactly the same on both sides? Yeah, and when you get done here, we should have the charges add up to the same on both sides, but we have a sulfate that's the same on both sides. Is that it? That's it. We can eliminate that. What's left is going to be our net ionic. So the OWL answer to this is going to be, and they want all of these aqueous and solids in there, because your zinc on this side is a solid, but on this side it's an ion. So OWL's looking for this Zn solid plus Cu2 plus aqueous, Zn2 plus aqueous, and Cu solid. That's what OWL is looking for. The tricky ones are if you have an acid, and then you got to figure out if it's strong or weak, which is the next example. But that should get you, remember, you can click into OWL part 2 and write out that names of acids easily. Then on this quiz, try to work on the first 12. You got to balance some, they're going to be double replacement, they're going to be net ionic. Try to work on the first 12 and work on OWL.